Mohan sir, good morning.
Good morning. Good morning, Bruce.
HOD sir, ஆரம்பிக்கிறீங்களா?
Available, sir.
Sir, good morning, sir.
Good morning. Good morning.
Good morning to all. I feel immense pleasure in delivering a welcome address of this 3-day international webinar on Frontiers in Chemical Sciences, FCS 2020. On behalf of Department of Chemistry, Bharatiya University, I extend my welcome to our Honorable Vice Chancellor, Professor Dr. P. Kalidas sir, who supported and encouraged us to conduct this webinar. Our Vice Chancellor has a rich teaching and research experience of 31 years. Formerly, he was the ICMR Emeritus Medical Scientist in the Center for Biotechnology, Anna University, and he also served as an officiating Vice Chancellor at Anna University. He has published more than 88 research articles and have 3 patents. He also developed 3 products. He has successfully guided 42 research scholars and received many awards, including the Lifetime Achievement Award from the Biotechnology Research Society of India in the year 2013. He had operated many research projects funded by various funding agencies like ICMR, CSIR, DBT, UGC, etc. He also collaborated with foreign institutions. With these few words, I welcome you, sir. And I am very happy to welcome our respected Professor Dr. K. Murugan, Registrar in charge, Bharatiya University. He has given constant support and encouragement in various aspects. He has 30 years of research and teaching experience. He served as an additional director, DRDO BUCLS, and has been the Vice Chancellor of Tiruvallur University, Vellore, Tamil Nadu. He also served as the Vice Chairman for the Tamil Nadu Science and Technology Centers, Department of Higher Education, Government of Tamil Nadu, India, and he has published more than 450 research papers and produced 50 PhD research scholars. With these few words, I welcome you, sir. I extend my welcome to our invited speakers, Dr. M. Sangaralingam, Assistant Professor, Department of Chemistry, NIT Calicut, and Dr. Sundaravel from Goa University, and Dr. Sugandha Mantal from IIT Kharagpur, and Dr. Anirban Chandra from Germany, and Dr. K. Gopalsamy from Melbourne, and Dr. S.J. Anandakrishnan from Texas, and Dr. M. Balamurugan from South Korea. On behalf of our department, I welcome you all. Further, it gives me a great pleasure to welcome the entire active participants for this webinar. Next, I am very happy to welcome our department colleagues and our former head of the department, Professor P.S. Mohan. At this juncture, I feel free to say a few words about our department. The department started functioning as PG Center of University of Madras. Then from 1982, it came under Bharatiya University. Our department offers MSc, MPhil and PhD programs. The department has 10 faculty members who are intensively involved in teaching and research in the diverse fields such as biomimetic and bio-inspired catalysis, metallotrucks, nanomaterials, organic synthesis, and supramolecular chemistry. To its credit, the department has several major and minor research projects funded by various agencies such as UGC, CSIR, DST Serv, DRDO, etc. to the tune of crores. In the past 5 years, our department has published more than 500 international publications and in totally produced nearly 150 research scholars. The department is in active collaboration with industries, national, international institutes and industries to produce valuable outputs. Once again, I welcome you all for the international webinar FCS 2020. Welcome you, sir. Thank you. Now, okay.
Now inaugural address will be given by Professor P. Kaliraj, Honorable Vice Chancellor, Bharatiya University.
Thank you. Good morning, all. Respected Professor Dr. P.S. Mohan, former head of the Department of Chemistry and our syndicate member now, Dr. Murugan, our registrar, Dr. M. Ilanjalian, the present head of the Department of Chemistry, organizing secretary, Dr. K. Sundaravel, and other organizing committee members, Dr. Selvaraju, Prabhakaran, Kaveri, Murugesa Pandian, Suresh, Kannan, Karthik, and the resource persons from the reputed laboratories, Dr. M. Sangarlingam, Dr. Duri, Dr. Mandal, Dr. Chandra, Dr. Gopal Swami, Dr. Anandakrishnan, Dr. Balamurugan. I welcome you all for this 3-day international webinar on Frontiers in Chemical Sciences, FCS 2020. At this moment, I am proud to note the chemistry department of Bharatiya University, originally originated from Madras University as a PG center. But I would like to express my concern why it is not accepting the interdisciplinary research. I should see a faculty with a biochemistry background, a faculty with a molecular biology background, and a faculty with a microbiology background. Now, without chemistry, nothing can move. Basically, I am a chemist, BSc chemistry, but I did not have the mathematics background. I was rejected by the chemistry department, not given me the MSc chemistry. There is a genuine reason for that, because without mathematics, we can't do that. So I had to go for MSc biochemistry. Then after that, I was rejected by Dr. G.N. Ramachandran, though I have passed in the written examination for PhD in Indian Institute of Science. I performed well in the interview, and G.N. Ramachandran told, "Gentlemen, I understand that you read my research work and you have performed well in the interview, but I will not select you." Again, he told, "I don't have mathematics background." Okay. Now the question is, it's not possible for everyone with strength in a particular subject. Now, the chemistry department of Bharatiya University, and in most of the universities, they don't allow any student from other discipline to do PhD with them. I fight with them. I will change it. At least before I leave, I will make it as interdisciplinary. I will violate whatever norms you are having it now. Now, the chemistry department, the individuals with chemistry background, you will be the more ideal person to work with the people with the biochemistry background and molecular biology background and bringing the research the best possible way. Dr. Ilanjalian has prepared a research project that is on to take the drug which has failed in the phase 3 clinical trial, go for artificial intelligence and identify the analogs of those compounds. It might have failed in the phase 3 clinical trial for some other disease, so they want to go for COVID. So you need a person with the bioinformatics background. Then you are going to do the synthesis as well as identification of the active compound for the COVID. Then it has to be evaluated with a microbiologist and all. So I want the faculty members from the chemistry department, they should take the student from other discipline. You can have a co-guide, and your department itself will be able to produce the result much faster than what can be done by the molecular biology department or microbiology department. Because without chemistry knowledge, you cannot do anything. Whatever the little knowledge I had at the level of BSc chemistry, I was able to understand the molecular biology, then recombinant DNA technology oriented one, and it was possible for me because of my chemistry background. So the person with MSc chemistry background, PhD chemistry background, they will be adopt all kinds of technology if you are having some students. Most of the time, we learn from our students. It's not possible for us to adopt everything now because whatever the technology that we had at the time of we completed PhD, it is obsolete now. You have to learn from the students. So you need students with various background, and you have to develop various things like developing recombinant proteins for diagnostics, then for the vaccine development, mostly drug targeting. The drug targeting is a very important aspect. As a chemist, you should be able to crystallize with the support of a person with the biophysics background, and you can reduce the structure, you can synthesize that, and you can modify that, and you can go for the evaluation. So lot many expectations are there for the chemistry. I am very specifically telling about Bharatiya University because I am selfish, and it has been developed by so many stalwarts, including Dr. P.S. Mohan. Now currently Dr. Ilanjalin is doing very well, and I want this department to go for the multidisciplinary work, and whatever the work which can be done by the people in 10 years, you will be able to do it in 1 year or 2 years. So that's the way we want to have for the multidisciplinary, interinstitutional project, and going for the projects of various kind through DRDO and other funding agencies. I'm happy this international seminar has targeted a good number of people, starting with the junior people like Dr. K. Gopal Swami, he is only as a research assistant, and a postdoctoral fellow, Dr. Ananda Krishnan, and Dr. Balamurugan, who is a research assistant professor. These are the people, they will be knowing the modern developments. If you take a professor of my age or Dr. P.S. Mohan age, our era is different. We might update our knowledge, but the impact will be more when it is explained by the person who is exercising that. And these are the people who might be doing the innovative work in chemical sciences in the best possible manner. You have Dr. Anirban Chandra from who is from Humboldt. Then you have an assistant professor Mandal, Dr. Sundaravel. All people are youngsters. They are the right people to tell about the frontiers in chemistry. So I request these young people to emphasize the importance of interdisciplinary subject, how you are going to link your chemistry with bioinformatics, chemistry with molecular biology, chemistry with various other subjects like environment and all those things. I hope this particular international webinar bring the collaboration among yourself. Nowadays, we have a very good possibility for interacting ourselves through online to start with. Then we can go for an international project, starting with the fellowship programs, then for the international projects. And you have a lot of money in the government of India itself. A good project will be, considered by all kinds of funding agencies. So I hope this program will be really successful. It is not listening alone. I want this to make us an international collaborative one. At least 2 or 3 of the chemistry department faculty members join with these experts from various academic institutions, start some new projects or program at the end of these things. And also you give some time for the discussion or interpretation or the collaborative talk as a part of this particular program. I wish the program all success. I wish I congratulate Dr. Ilanjalian for making such a wonderful arrangement. Thank you for the participation of Dr. P.S. Mohan, who has done a lot in chemistry. I wish that he will continue to make this department to come to the next level. What you have seen as a chemistry those days is different. What we would like to see is different. I want a vaccine to be developed by a chemistry department. I want a diagnostic target to be this one by chemistry department. I want a drug target for COVID-19 or any one of the infectious diseases, which is a subject of global as well as for the India, especially for tropical diseases, infectious diseases pertaining to the tropical diseases, where Western countries are not interested. But it is our responsibility to go for developing some drugs for the infectious diseases. I hope the chemistry department will come out in a big possible way. Thank you very much for giving the support. Thank you.
Thank you, sir, for inaugurating the webinar. Felicitation address will be given by Professor Dr. K. Morgan, Registrar in Charge, Bharatiyar University.
Very good morning to everybody. The most honorable Vice Chancellor, Professor Dr. Kaliraj, even though his busy schedule, he has inaugurated this conference so that the Bharatiyar University Chemistry Department is very happy about our honorable Vice Chancellor. He is leaving to other place for his official business. But even though he has participated, I am also very happy about that. And respected Dr. Ilanjalian, the Associate Professor, Head the Department of Chemistry, Dr. Mohan sir, the former head of the Department of Chemistry, and he is a senior most professor. And also happy to note that he is our syndicate member for 3 years. And really, he will be associating with our Vice Chancellor. He will be associating with our Department of Chemistry and all the people, and his tenure will be most successful for our university. And also I thank Mr. Sundaravel, Assistant Professor, Department of Chemistry, Bharatiyar University, and all other young resource persons from various countries, all from our Tamil people. They have working in abroad, and they are very busy and very intellectual people. They are giving a very good lecture on the frontiers in chemical sciences. As our Professor Dr. Kaliraj, our Honorable Vice Chancellor, said that is chemical sciences is a major subject for each and every science, not only a science, also in a social science, also even psychology people also interrelated with the psychology in relation to the various physico-chemical aspects of human being and other even social behavior of animals in chemical point of view. So that it is as our Professor Dr. Kaliraj sir said that chemical sciences is interdisciplinary as well as multidisciplinary. At this juncture, I congratulate Dr. Ilanjalian, Professor Dr. Mohan sir, former head of the department, and all other staff members in this chemistry department. I wish this conference will be success, and thank you very much. Thank you, one and all. Thank you very much.
Thank you, sir, for felicitating the webinar. Now, the vote of thanks will be given by Dr. K. Sundaravel, Organizing Secretary, Assistant Professor, Department of Chemistry, Bharatiyar University.
So very good morning to one and all. It's my pleasure to propose the vote of thanks in this webinar. So before proposing the vote of thanks, I would say some of the glimpse about the webinar. There is a Frontiers in Chemical Sciences. The webinar is arranged in such a way to bring the people from various fields of chemistry. So on behalf of the chemistry department and Bharatiyar University, I invite you all for the 3-day international webinar on Frontiers in Chemical Sciences. There are 7 eminent personalities from different fields of chemistry are going to deliver lecture throughout the 3 days program in the following topic: water oxidation, medicinal photonic materials, biomimetic and bio-inspired catalysis, and the electrochemical reduction of CO2 and gas molecule separation by metal organic frameworks. So I am sure that this 3-day international webinar will disseminate knowledge on the development of precise molecular probes to solve the existing puzzles, and it would be highly useful for the society also. This event also aims to promote high quality research in the field of medicine, catalysis, and synthesis of selective organic molecules using metal catalyst. Indeed, I wish to mark here that about 500 participants have registered for this webinar. Once again, I warmly welcome you all for this 3 days international webinar on frontier chemical sciences. Thank you. And what of thanks, it is my pleasure, most respected Honorable Vice Chancellor, Bharatiya University, Dr. P. Kaliraj sir, most respected Professor Dr. R. Murugan sir, Registrar in Charge, Bharatiya University, and Professor Dr. M. Nilanjalian, and Professor Dr. Mohan, retired, convener of this webinar, my dear colleagues, distinguished participants, and research scholars and student friends. Very good morning to all. I feel honored and privileged to get an opportunity to propose a vote of thanks on this occasion. I, on behalf of the Department of Chemistry and on my own behalf, convey my deep regards and heartfelt thanks to Professor Dr. P. Kaliraj, Honorable Vice Chancellor, Bharatiya University, for his gracious presence in the inaugural function and sharing his knowledge with us, his vision of basic and applied technology in chemical sciences. At the outset, I record my sincere gratitude to Professor Dr. K. Murugan sir, Registrar in Charge, Bharatiya University, for his constant support and encouragement and his valuable felicitation address. My profound thanks and gratitude are due to Dr. M. Nilanjalian, Associate Professor, Head, Department of Chemistry, Bharatiya University, for adding new dimensions for the successful organization of this webinar, FCS 2020. On behalf of the Chemistry Department, I shower my heartfelt thanks to all and gratitude to all staff members of Chemistry for their wholehearted support, dedication, and teamwork rendered to us. My special thanks to the eminent speakers, Dr. Sangaralingam, Dr. Sundaran Duri, Dr. Sugata Mantal, Dr. Anirban Chandra, Dr. Gopal Swami, Dr. Anantakrishnan, and Dr. Balamurugan. They are working in the various frontier fields of the chemistry, who are going to deliver their valuable research findings with us. I convey my special thanks to all distinguished participants who have participated in this webinar from different disciplines of science across the globe. I hope that this international webinar definitely fruitful to gain more knowledge and to promote high quality research in the field of health, agriculture, and environment sectors. My special thanks all the committee members of the Department of Chemistry and other faculty members, and one of my friend Dr. P. Kuru Saravanan from the Department of Botany, and also I thank my research scholars and research scholars from our department also for their constant support. I also thank the non-teaching staff members, Mrs. Nityakala, Mr. Balamurugan, and Mailsami for their support throughout the program. Once again, I thank all for the participating in this webinar, international webinar. Thank you, one and all. So may I now request Dr. R. Prabhakaran to introduce the speaker. The session will continuously start from the inaugural function. Yeah, thank you.
Thank you, Dr. Sundaravel. It gives me an immense pleasure in inviting our resource person, Dr. M. Sangaralingam. He is working as Assistant Professor of Chemistry at National Institute of Technology, Calicut. For his credential, Dr. Sangaralingam did his PhD with Professor Palniyandavar sir in Bharathidasan University. And he has been working as Senior Research Fellow at IIT Madras with Professor Anbarzen. Then he was doing his postdoctoral research work with one of the famous scientists, Professor Won Nam at Eva Women's University, South Korea. And he is a recipient of DST Inspire Faculty Award for Chemical Sciences in 2018 to 2023. Currently, he is holding a position of Assistant Professor at National Institute of Technology, Calicut. For his credentials, he is one of the leading scientists in his area of research, and he published more than 30 research articles with the impact factors, average impact factor of 6.1. Further, it is a note to mention here, he has published more than 7 international research articles in JAX and Wendy with the impact factor of more than 10. It would be of much more appreciable, and of course, it would be of an inspiring one for the participants who are participating. And he is currently having 2 PhD students and having 2 funded research projects. Within this brief introduction, I welcome Dr. Sundaravel to take over the session and to discuss his expertise with the participant. Thank you very much.
So, first of all, I would like to thank the organizers and convener, Dr. Sundaravel, who has invited me to give a lecture in this webinars, international webinar session. So I hope I am audible to all of you.
Yes, you are audible.
Okay, fine. Thank you. So thank you, sir, for your kind introduction about me. So let me start my presentation. So let me share my presentation now.
Pleasure, please.
Yeah. So can you see my slide? That's fine. So my slides are visible. Okay, fine. Thank you. Yeah. Okay. So as Dr. Prabhakaran introduced about me, so I have done some bioinorganic chemistry work, and this today's lecture, so I will be discussing about the recent findings which I have done it in my postdoc, and what I am doing it here. Okay, so that I will be discussing, and this is one of my research area what I would like to discuss with you. So today I will be focusing more about the synthetic high valent manganese oxygen intermediates which are involved in photosynthesis reaction, that especially photosystem 2, that is oxygen evolving complex. Okay, so before I would like to go into my lecture, so I would like to give you some brief introduction about our NIT and our department. So this is our the entrance of our NIT Calicut. So by this way you can come inside, and we have academic campus, and opposite to this we have the residential campus. So we have a 3 campus, so academic campus and east campus. East campus is the chemistry department is there. Okay, so yeah. So this is our chemistry department, which is situated in the east campus, and it's very beautiful. Completely, it is greenish, and this was sketched by one of our adjunct staff. So that is Mr. Sajesh. Okay, so in case if you did, sorry. Yeah. So in case if you did not visit NIT Calicut as a student, so you have still more possibility to visit NIT Calicut after your BSc course. You can join here as an MSc student by clearing JAM exam, and the national counseling you have to admit, and then you have to come here for your MSc chemistry program. Okay, so then okay, so still if you miss an opportunity to study here as an MSc student, still if you are doing MSc program in some other universities or some other college during your first year program, right after your first year program, so you can apply here as a summer internship. So we are offering this for the first year MSc course. So you can apply to our institute, and you will be undergoing some scrutiny, and then some qualifications will be there. So based on that, you will be called for a summer internship. So then still if you miss an opportunity to visit NIT Calicut, so you can join as a PhD student after your MSc, program. So you can with the qualification of GATE or CSE or JRF or UGC JRF or in fact DST JRF. So with this, I would like to go into the details of my lecture and whatever I have done it recently, that highlights I will be discussing with you. And this is before I would like to go into the lecture. So I would like to acknowledge, I would like to give an acknowledge to my professors. So this is my postdoc professor, Professor Wanwu Nam and Professor Fukusumi. They introduced me to the field of biomimetic inorganic chemistry and the topic which I am going to discuss today. Okay. And apart from that, I would like to thank the collaborators, Professor Yang Min Lee and Professor Elio Puskar and Cheng Ming Lee and Dr. Duri and Dr. Mail Murugan. And of course, for the funding. So for NIT Calicut, so faculty research grant and the DST Inspire Faculty Award. Okay. So I believe that there must be some BSc chemistry students as well as MSc students. So I prepared some basic introduction about the bioinorganic chemistry. So you can see in this slide, so bioinorganic chemistry. Yeah, let me take my pen. Yeah. So bioinorganic chemistry, actually it is a multidisciplinary field which covers physics and chemistry and medicines, a lot of fields. You know, it is beautifully integrates the chemistry, physics, molecular biology, and protein science, even environmental science. Okay, so what you are going to study after this bioinorganic chemistry as a bioinorganic chemist or biomimetic chemist? So what you are going to do after learning these things? Okay, so from this pictogram, one can understand simply. So I will explain to you. You can follow me. So the nature has a variety of enzymes, proteins, and metal ions. All those metal ions are there. So first you need to search and first you need to find out what are all the metals or metal ions or proteins or enzymes which are present in the nature, and you have to study that. You have to study that, and after studying, you will be gaining a knowledge, and that knowledge, and you have to think with that knowledge you can use for the human applications. Okay, so simply I can return here. So search and study the things which are created by the mother nature and use the knowledge gained to the human applications. Okay, so then, so with this introduction of bioinorganic chemistry and bioinorganic chemist, so I would like to share you the notable example. So in 2018, so we got the Nobel Prize for bioinorganic chemistry. Professor Francis Arnold, she got the Nobel Prize for the directed evolution of enzyme, and along with the Professor Smith and Professor Winter, they have actually worked on the phage display of peptides and antibodies. Okay, so mainly I will be discussing about the Professor Francis Arnold, that she has actually worked on the directed evolution of enzymes. So I will discuss with you what is directed evolution of enzyme. Okay, so before I go into that, so what are all the enzymes which is actually useful in our life in a fundamental way? Okay, so that I will be discussing in the next one slide. So I focused mainly on the heme binding proteins. So heme binding proteins, it's a very important protein is hemoglobin and myoglobin. So where this oxygen is carried from lungs and it is transported to the tissues, and this oxygen, the hemoglobin is an oxygen carrier, and myoglobin is an oxygen storage protein. Okay, so this can do a specific functions, right? Like oxygen carrier and oxygen storage protein, right? So similarly, there are other proteins. So that is another one is cytochrome C oxidase. So this also contains a heme protein, so a heme coordination. You can see here, so you have iron center, which is surrounded by the porphyrin nitrogens, and in the axial position, you have a histidine nitrogen. And apart from that, you have a mononuclear copper center. So in this active sites, in this site, cytochrome C oxidase, so what it will do is that the oxygen will be reduced to water. That is a 4 electron, 4 proton reduction. It is happening here. So once you inhale the oxygen here, and whatever it is stored here, so that will be converted to water by this protein during the respiration chain. Okay, so then after this, there is another unique protein. So that is cytochrome P450. So the cytochrome P450, again, this protein is also contains iron in the active site center, and you have oxygen coordination, and this performs a variety of reactions such as organic transformation reactions like epoxidation reaction, sulfoxidation reaction, hydroxylation reactions, ND alkylation. So there are many reactions. Okay, but what is the main intermediate which is involved? Okay, so these three proteins are very unique, and for example, this first two proteins which will be doing oxygen carrier and oxygen transport, oxygen storage protein, and this protein is involved for the oxygen reduction to water, and this is for the organic transformation. So Professor Arnold focused on this portion. So you can see here, so the cytochrome P450, this is a catalytic cycle of cytochrome P450. You have iron 3 in the active site, and you have cysteine sulfur, and the sixth coordination will be water. So when you add alkane, so the water will be removed, and this alkane will be coordinated through the protein chain with the hydrophobic interaction. And this iron 3 has been confirmed by EPR spectroscopy, and from that they understood that it is a low spin in oxidation state. And once this organic molecule, that's alkane, okay, when it binds to the hydrophobic unit, so this spin state of this iron 3, it changes to the high spin. From low spin to it changes to the high spin. So now it accepts an electron from FADH2, okay. And as well as if you look at the redox potential of this compound 1 and the compound 2, upon binding of this substrate, organic substrate, the potential is drastically increased from -300 to -173 millivolt. Okay. So what happened? This FADH2 is donating an electron to this iron 3. So it is accepting an electron to become iron 2 high spin. Iron 2 high spin. So now this iron 2 high spin, which will react with the O2. So this iron 2 will donate one electron to O2. So you know that O2 has a 2 unpaired electrons. So this can accept one electron to become superoxide radical anion. So it becomes superoxide radical anion. So this radical anion is stabilized by the hydrogen bonding with threonine amino acid. Okay. And further it can accept electron and proton to become peroxide and hydroperoxide. And this hydroperoxide undergo O bond cleavage to become a very reactive intermediate, that is iron 4-oxoporphyrin pication radical. This is compound. This is called compound 1, and this hydroperoxide is called compound 0. And this very reactive intermediate, it can react with alkene or olefin or amine. So it can oxidize the substrates, the respective substrates. So for example, here alkane is there. So this is oxidizing alkane to get alcohol. Okay, and you get the compound 2 as a another product, that's a iron 4 hydroxo. Recent days it is believed that it should be iron 4 oxo. Okay, so the reason I discussed with you here, so this iron 4 oxoporphyrin pication radical, it will react with olefin, and you will end up with the epoxide through the concerted reaction mechanism by this way. You can see here, so this is iron 3. Actually, you formed iron 4-oxoporphyrin pication radical, so which is reacting with the olefin, and through the concerted reaction pathway, so you get a epoxide as a product. Okay. However, Professor Arnold focus, so generally, if you take any olefin, if it is undergoing Markovnikov reaction or anti-Markovnikov reaction, so this is the products you will get. So if you get this product, so this is corresponding to the Markovnikov reaction, and this is for the anti-Markovnikov product. Okay. Same reactions, if you perform in the presence of metal oxo, so you will end up with the epoxide. Okay, so this is the case. It happens in the cytochrome P450, this epoxidation cycle, the blue color which we have mentioned here. Okay, but one can control the interaction of this olefin with this iron oxo. Okay, in such a way that this olefin will generate a carbocation radical, and if you can stabilize the carbocation radical, so then you can transfer this hydride. So this hydride will undergo transformation, and you will end up with the anti-Markovnikov product. Okay, so this is anti-Markovnikov product which was obtained by the metal oxo mediated enzyme catalysis, and for this specific work, Madam Professor Arnold, she got the Nobel Prize. And how she did it? How she has achieved this? By using 12 metal oxo units. So you have, if you look at this structure, so you have a 12 red color center is there. So if you count the number of the red color, so that is 12. So those 12 are 12 metal centers. So 12 metal mediated oxo can form, and then you can actually stabilize the carbocation radical formation, and you can finally end up with the anti-Markovnikov product by a selective reaction. Okay, so this is one of the very inspiring work of biomimetic inorganic chemistry. So that with this, I would like to move on to the photosynthesis introduction. So so this is very famous reactions. So this one, so carbon dioxide react with the water in the presence of light and with the plant pigments, and you will end up with the glucose and O2. So the water will be converted to O2 and carbon dioxide will be converted to the glucose in the presence of light. And this forward reaction is called photosynthesis, right? So again, this glucose and O2 will be utilized during the respiration, and from the glucose you produce ATP, and this oxygen again it will convert to water. Okay, so this is a respiration reaction. So how this water is getting oxidized to O2? So this is my interest. Okay, so this how this water is getting oxidized to O2. So in photosynthesis, so there is a another complex. That complex is called oxygen evolving complex. So which has a 4 manganese, 1 calcium, and 5 oxygen in their active site. So this is the active site center of oxygen evolving complex, and this purple color is manganese, and this red color is oxygen, and you have a golden color, and this golden 4 golden colors are there, and these 4 golden colors are water molecule. Okay, it is believed at the beginning it is a water molecule. Okay, and this has been reported in many science and nature journals. Okay, and this was one of the proposed mechanism, and which was proposed much earlier, and this is known as Koch cycle. So it was believed at the beginning that the initial compound it must be having a manganese 2 center, and you have 2 water molecule, and calcium 2 you have a 2 water molecule, and you have a glutamate amino acid chains which is connected. Okay, and you have a bis-myoxo bridged center is also there. So if you look at here, so there is a loss of proton and electron. That's a successive loss of proton and electron in all these cycles. So if you look at here perfectly, so that manganese 2 water molecule, it is transformed to manganese 3 hydroxo by losing 1 proton and 1 electron. Further loss of 1 proton and 1 electron, it forms manganese 4 oxo, and further loss of 1 more electron. So the manganese 4 oxo will become manganese 5 oxo, and this manganese 5 oxo is believed to be a very reactive compound, and which will abstract a hydrogen from the water molecule which is bound to the calcium unit. And now at this position, so there will be a O bond formation. So it occurs here. Okay, so when there is a O bond formation, so you will get the manganese 3 hydroxo, manganese 3 hydroperoxide intermediate, and further loss of electron and protons. So you will release O2, and you will generate again the resting state. So what is the overall reaction? So overall reaction is 2 equivalents of water which is converted to O2, and plus 4 proton and 4 electron is formed. Okay, and if you look at in this catalytic cycle, so this is a very simple catalytic cycle which was proposed much earlier, and recently updated cycle is there that I will be showing you in the next slide. So what are all the intermediates which are involved? So if you look at that, you can see manganese 2 aqua compound, and manganese 3 hydroxo compound, and manganese 4 oxo, and manganese 5 oxo, and manganese 3 hydroperoxo, apart from the bis-myoxo manganese 3,4 center. Okay, so I was interested to make all these intermediate in a synthetic method by using a mononuclear manganese 2 compound. Let me show you whether I am successful in making all these intermediate or not. That I will be showing in the next slides. Okay, so the recently updated cycle for the oxidation of water to O2 in OEC that has been proposed very recently. Okay, so very recently it has been proposed this among the 4 manganese. If you follow my cursor, you can understand. So among the 4 manganese, so you will be having a 3 manganese in +3 in oxidation state, and 1 manganese which has a +4 in oxidation state. However, if you look at in my previous slide, so I did not mention for oxidation states for the other manganese center, because that was proposed much earlier. Okay, so this is a very recent one. So here, if you look at, there is a hydroxo unit instead of 2 water molecule, and you have a 1 hydroxo unit, and loss of electron and proton, you produce another manganese 4 unit with the oxo bridged compound. So now if you see that in S1 state, there are 2 manganese which has a +4 in oxidation state, and 2 manganese which has a +3 in oxidation state with the spin state of S equal to 0. Okay, and further loss of 1 more electron to become S2 state. In the S2 state, what happens? So 3 manganese which is present in +4 in oxidation state, and 1 manganese which is present in the +3 in oxidation state. And in this case, after this step, so again loss of 1 more proton and 1 more electron and proton by the addition of water, you will get all the manganese which is converted to +4 in oxidation state. Okay, so now what happened? So after this, already all this manganese has been oxidized to +4 in oxidation state. So which means further loss of proton or electron, either you're supposed to get a manganese 5 oxo unit, or one of these manganese should get oxidized to manganese 5, or this either this hydroxo unit or this oxo unit, it should become oxyl radical. Okay, so that is what this still this S4 and S4 prime state, it is actually not experimentally observed. So this is a proposed state, and the proposed state has a manganese 4 oxyl and manganese 5 oxo. Either it can be manganese 4 oxyl or it can be manganese 5 oxo. And based on this, there are many different mechanism has been proposed for the O-bond reaction, and two of the pathway is very well accepted one, that is oxyl oxo coupling. So oxyl oxo coupling, that is this one. So this oxyl and oxo coupling to form a O-bond, or this water attack to this manganese oxo, manganese 5 oxo through the nucleophilic attack. Okay, so this is a very well accepted pathway of this. Apart from that, there are some other pathways also there. So that's I did not focus much. Okay. So based on this, again, I mentioned that there are many different intermediates which are involved, and my focus is to make a mononuclear synthesis, mononuclear manganese oxygen intermediate. Mononuclear oxygen intermediate. So that is this way. So you can see that I call it as biomimetic manganese oxygen intermediate or synthetic manganese oxygen intermediate. So for this study, so mainly I specifically focused on this manganese DPAQ complex. Okay, so I mentioned here DPAQ complex. So at the beginning, I synthesized the manganese 2 DPAQ complex, and when I exposed that manganese 2 DPAQ complex to O2, and it forms manganese 3 hydroxo in acetonitrile medium. And this compound has been crystallized, and it has been characterized by ESI mass spectra, ESI mass and EPR spectroscopy and UV spectroscopy, and as well as Evans method to find out the spin state of this manganese 3 hydroxo. And after having this manganese 3 hydroxo, what I did is that I just added 1 equivalent of proton, whether I can get manganese 3 aqua compound or not. So I added 1 equivalent of proton, so I got manganese 3 aqua compound. And this manganese 3 aqua compound shows a very good reactivity with the OH1 reaction and electron transfer reaction. So this is the first example to show that manganese 3 compound can be a potent oxidant for a variety of reactions. Okay, and after having this manganese 3 hydroxo, again I thought, okay, I can produce a manganese 4 oxo simple manganese 4 oxo compound. So I added PHIO to this, but I didn't get the manganese 4 oxo. Instead, I got a dimeric species, manganese 3,4 bis oxo dimeric species. And again, this is one of the intermediate which is there in the oxygen evolving complex, and this particular compound shows a variety of reactions like amphoteric in nature. Amphoteric in nature means, you know, it can actually behave like a nucleophilic character as well as electrophilic character. It can have a both androgynous character. Okay, so then the same reaction I performed in the presence of a metal ion. So a redox inactive metal ion starting from the scandium to calcium ion. So I end up with the metal ion bounded manganese oxo compound. Okay, so to this metal ion bounded manganese oxo compound, I added a cerium. That's a redox active metal ion. Okay, I added a cerium. So now I could produce a redox active metal ion bounded manganese 4 oxo intermediate. Okay, interestingly, if you look at these two structures, you know, this is the only example so far in the literatures where you can have a variety of metal ion which can bind with the manganese oxo compound. So starting from calcium to scandium. Okay, so we took an advantage of this particular ligand system, and we performed many different reactions, and we succeeded in those reactions, and we published several interesting articles. So I will show you the highlights of these particular reactions in the next slides. So after this, you know, this is very famous ligand which was made by Professor Collins, and this is a tetraamido macrocyclic ligand. So I used this iron and manganese complexes to produce iron 5-oxo and manganese 5-oxo compound. So this especially here I mentioned the manganese 5-oxo because I mainly focused here on the manganese oxygen intermediate. Okay, so here manganese 3 compound, I have taken it and I used oxygen as an oxidant, molecular oxygen as an oxidant, and in the presence of olefin, it produced manganese 5 oxide intermediate. And the results has been published in these journals. And this is a special ligand where you can stabilize a trigonal bipyramidal geometry. And with this particular ligand, a manganese 4 peroxo compound, which has been already reported by another group, our collaborator Professor Lee, and we took that peroxo and we try to see whether we can produce a manganese 4 hydroperoxo unit or not. So that also we could achieve. And after this, so many manganese peroxo compound has been reported by using hydrogen peroxide triethylamine method, but there are very limited manganese peroxo compound which has been reported by using oxygen, dioxygen as an oxidant. So I was thinking whether I could make manganese 3 peroxo with the dioxygen or not. So then I selected this particular tetramethyl cyclam ligand and I added oxygen to this particular compound in the presence of triethylamine as an electron donor. So I got manganese 3 peroxo compound, and then addition of proton, I end up with the manganese 3 hydroperoxo compound. And this is the second example of manganese 3 hydroperoxo compound, which is known in the literature. Okay, so I will briefly explain you the highlights of these particular reactions in the next slides. Okay, so as I mentioned to you that I made a manganese 3 compound and I exposed to O2 in the presence of acetonitrile as a solvent. I end up with the manganese 3 hydroxo, and upon addition of proton, I form manganese 3 hydroxo, and upon removal of this proton by using a base triethylamine, I can get a manganese 3 hydroxo unit. So this reaction is reversible in nature. And if you look at here, so the redox potential I have determined by using cyclic voltammetry as well as the spectral redox titration method. So cyclic voltammetry, from this compound we have determined the reduction potential by using cyclic voltammetry, and the reduction potential it shows minus 0.1 volt versus saturated column electrode. And when I add one proton, interestingly, if you look at here, the potential it is changing from minus 0.1 volt to plus 1.03 volt. It's nearly 1 volt difference is there. So then we were thinking that okay, this compound whether we can use for an oxidation reactions or not. So then at the beginning, I try to do some electron transfer reactions, and it works very well because it has a very high reduction potential. Okay, and this one I could not determine the reduction potential by using cyclic voltammetry because the electrode is irreversible. Okay, one electrode is irreversible, so I could not determine. So I used the spectral redox titration method to find out this potential. And then I have used a variety of substrates that's a OH bond activation and CH bond activation. So we found a very interesting reactivities. And before that, I will show you that characterization of these two intermediates. You can see here. So this red color. So the red color is actually the manganese 3 hydroxo compound. Upon addition of one equivalent of proton, so the red color it is changing to the blue color. This is a UV visual spectrum. So the red color it is changing to the blue color. So the insert shows just the conversion, reversibility. Okay, so the reversibility of this particular reaction. Upon adding proton and addition of base, I can reproduce. I can interplay with these two intermediates. Okay, so then very strong evidence. I got the crystal structure. So I have a manganese 3 hydroxo crystal structure and manganese 3 aqua compound crystal structure. Interestingly, if you look at very carefully, this manganese oxygen intermediate, the bond distance, it is 1.8 Armstrong here, and this is 1.94 Armstrong in the aqua compound. Okay, so this is quite obvious because this aqua compound, you have addition of proton, that means it weakens the manganese oxygen bond length. Okay, so now we have characterized and we subjected this for variety of reactions, and we also determined the oxidation potential of these substrates, and we know the reduction potential of this intermediate. Then we try to utilize a well-known equation, Marcus equation, okay, to see whether our reaction is proceeding through an electron transfer reaction or a specific hydrogen atom transfer reaction. So for that, first we calculated the driving force constant. The driving force constant. So this is the formula minus delta EGT, which is equal to E reduction potential minus E oxidation potential. So we calculated the reduction potential of our intermediate. So that is 1.03 volt versus SCE, and oxidation potential of these substrates. So here I have listed out here These red colors are the like electron donor substrates, so dibromoferrocene, diacylferrocene, and this oxidation potential is already known in the literature. So we have taken it from the literature. And this black color, so black color is the hydrogen atom transfer substrate. So that is a 2,6 ditertiary methoxyphenol and methylphenol substrate. So this 6 one is the methoxyphenol and 7 one is the methylphenol. Okay. Interestingly, if you look at this two substrate, okay, this is a OH1 substrate. Interestingly, if you look at these two substrates, it is parallel to the electron transfer reaction. So this red color, the red color line is suggesting that it's a pure electron donor substrate. So the red color one. So this is actually the black line is the very much parallel to this red color line. So which is indicating that. So these two substrates, the red remaining step is actually the electron transfer reaction followed by the proton transfer reaction. Okay. So then after this, we have used some, I have mentioned some blue color 8, 9, 10. So those 8, 9, 10s are actually 3,4-dimethoxytoluene and 2,4-ditertiary-butyl-phenol and xanthine. Okay, so if you look at these 3 points, okay, so these 3 points are uphill to the electron transfer reaction. So this is actually the red color line is the electron transfer line, and this is actually uphill to the this Marcus line. So therefore, this red constant, it is suggesting that these substrates are not following the electron transfer reaction. Instead, it is actually following the hydrogen atom transfer reaction. So that also has been confirmed by experimentally by the kinetic isotopic effect. So for the substrate 10, that is xanthine. So when we use the deuterated substrate, so we observe the kinetic isotopic effect of 3.9. So it is suggesting that so hydrogen atom transfer is the rate determining step. And there are some two purple color, the two pink color points are there, and this is for the substrate 5 on substrate 5 and substrate 6. So substrate 5 is octamethylferrocene and substrate 6 is actually again the methoxy substituted phenol. So these 2 points are corresponding to the manganese 3 hydroxo compound. So interestingly, if you look at this compound 5, okay, when we use the octamethylferrocene, so this is also fitting into the electron transfer line. So therefore, this is also a pure electron transfer reaction. However, if you look at this point number 6, the compound 2,6 ditertiary-butyl 4-methoxy-phenol. Okay, so this we observe the kinetic isotopic effect by experimentally 3.8, and which is very much uphill to the electron transfer line, and it is again suggesting that it is actually a hydrogen atom transfer reaction. Okay, so from this Marcus plot, so we can conclude that the driving force, what we have, the less than 0.2 electron volt, it follows the kinetic isotopic effect of 1, that is electron transfer followed by the proton transfer pathway, and whatever it has more than that, you follow the hydrogen atom transfer. That is first one is the proton abstraction and followed by the electron transfer reaction, or I can say that concerted proton electron transfer reaction. Okay, and this result we have published in JACS 2018. Okay, so then since I mentioned that we have the same compound in our hand, then I try to make the different metal ion bounded manganese oxo compound, the different reduction active metal ions, whether it can bind with this manganese oxo or not. So I used that this particular compound. So here, if you look at this diagram, this is a summary of this work. You have a manganese 3 hydroxo. If you when I perform this reaction with PHIO as an oxidant, only PHIO I formed a bis-mu-oxo dimer. Okay, only PHIO I form a bis-mu-oxo dimer. But in the presence of metal OTF, it is prohibiting, this metal OTF is prohibiting the formation of the dimer, and I end up with the mononuclear manganese 4-oxo compound. Okay, but it is not a only mononuclear manganese 4-oxo compound. Instead, it is actually the inactive metal ion bounded manganese 4-oxo compound. Okay, and now upon binding of this reduction active metal ion with the manganese oxo, it becomes a super oxidant to the sulfoxidation and CH1 activation substrates. Okay, however, this bis-mu-oxo manganese dimer intermediate, it doesn't show any reactivity with the same substrates. Okay, so inside there is a plot, and in this plot I have plotted the change in Lewis acidity of this different metal ion versus the versus the second order rate constants what I have collected it for the different reactions. So there are 3 different reactions which I mentioned here, that electron transfer reaction, the blue color, and oxygen atom transfer reaction, that is a red color, and hydrogen atom transfer reaction, that is a green color. So if you look at that electron transfer reaction and oxygen atom transfer reactions, which is very much parallel, so therefore this oxygen atom transfer, I can say that it follows through the electron transfer red remaining step. Okay. However, if you look at this hydrogen atom transfer reaction, so this is opposite to the oxygen atom transfer reaction. So then we were very much interested, because in the literature it is already known for the cytochrome P450. You know, I already mentioned to you that the cytochrome P450, in the axial position you have a cysteine sulfur amino acid. Okay, that's a very basic amino acid. So that basic actually it provides more electron to the iron center, and it can obstruct a strong CH bond. So that has been validated by a synthetic models by using a different axial ligand by this way. So it is already known. However, the binding of redox inactive metal ion or changing the Lewis acidity of this redox inactive metal ion, it is not known with the many different metal ions. It is not known. Only it is known with the scandium triflate binding compounds. Okay. However, this is the first example which we had shown from the calcium to scandium. So, for example, calcium has a Lewis acidity of 0.58 electron volt, whereas scandium has a Lewis acidity of 1.0 electron volt. Okay. So, therefore, this when you have a more Lewis acidity of this particular compound, okay, when you have a more Lewis acidity of this particular compound, it is actually not undergoing much faster hydrogen atom transfer reactions. However, if you have a strong basic metal oxo compound, that obstructs very strong CH bond, and you can see that this red constant is much faster than the scandium bounded compound. Okay, and that was our selling point. So we published this work in the JACS again. Okay, so yeah, so again, so since we have this particular compound, this reduction active manganese 4-oxo bounded compound, so we thought whether we can produce redox active metal ion compound or not. Okay, so we did many different reactions just by using only PHIO and PHIO metal ion. Okay, so PHIO metal ion we can produce many different metal oxo compound, and to this if we add CAN is ceric ammonium nitrate, so which has a +4 in oxidation state. Okay, so if we add ceric ammonium nitrate, whether we can produce a redox active metal ion or not. So, and then specifically we have done this particular reaction also, starting from manganese 3 hydroxo in the presence of water and ceric ammonium nitrate. So whether we can produce the cerium 4 bounded manganese 4-oxo compound or not. So we were able to successfully generate this intermediate, and we characterized this intermediate by a variety of spectroscopic techniques which I have mentioned here. So UV visible spectrum and EPR and CSI mass, resonance Raman, and XAS. Okay, and we have also performed the reactivities in electron transfer as well as oxygen atom transfer reactions and hydrogen atom transfer reactions. So you can see here. So here I just put only two UV visible spectra for the intermediate. So the black line is corresponding to the scandium bounded manganese 4-oxo compound, so which has a 700 nanometer, and upon addition of ceric ammonium nitrate to this intermediate, so it forms a cerium 4 bounded manganese 4-oxo intermediate. So you can see that this UV visible spectra, it is changed to another spectrum. The wavelength 700, it is transformed to, it is shifted to 740 nanometer. Then we were quite interested, quite interesting to characterize this intermediate by a variety of spectroscopic technique, and we characterized by resonance Raman also. So this is just one scandium. One scandium means scandium bounded manganese 4-oxo intermediate, and resonance Raman we can actually found this isotopically sensitive peak when we use the 18 labeled oxygen for this particular intermediate, and the difference between the 16 and 18 oxygen is 37 per centimeter, and which is consistent for the manganese oxygen double bond character. Okay, and to this, as I mentioned to you, that we have added ceric ammonium nitrate. So, and that also we have characterized by resonance Raman spectroscopy. And if you see that cerium bounded species, again it shows close to 30 per centimeter, and again these two numbers are quite close to that manganese double bond manganese oxygen double bond character. Okay, so I did not show you the EPR and CSI mass and other characterization because I thought it will be too much to discuss. So this is a fundamental one which we can confirm this manganese oxygen stretching frequency and the bond length. Okay, so then this binding of metal ion, cerium and scandium, that has been confirmed by mass spectrometry as well as the XAS spectroscopy. Okay, and so XAS spectroscopy, then we performed a variety of reactions. So now we were able to be successful in making the redox inactive metal ion bounded manganese 4-oxo compound as well as redox active metal ion bounded manganese 4-oxo compound. Okay, so then with this compound we were thinking what we can do further. So then, as I mentioned to you, that by the reaction of this compound with the aerosyl benzene, we can get PHIOs and we can get the dimeric compound, that's a manganese 3,4-oxo intermediate. Okay, we have also performed this reaction by using the hydrogen peroxide as an oxidant in the presence of triethylamine in acetonitrile at room temperature. Okay, then we end up with the bis-mioxo manganese 3,4 oxidation state compound. And we have characterized these particular compounds by UV visual spectroscopy. You can see this blue line is corresponding to this manganese 3-hydroxo compound, and upon addition of hydrogen peroxide and triethylamine, there is a new peak formation. So the peak is getting increased, and we get a solder peak around 540 nanometer. And this again, after forming this intermediate, we confirmed by CSI mass spectroscopy, CSI mass analysis, and it is confirming that the bis-mioxo manganese formation. Okay, and again we confirmed this by the EPS spectroscopy, and EPS spectroscopy, this is an experimental EPS spectra for the bis-mioxo compound, and it is clearly suggesting that we have a manganese 3 and manganese 4 unit which is antiferromagnetically coupled. So we get 21 lines of hyperpine spectra. Okay, and to confirm this, we simulated the spectra and we got the good simulation, and it is again confirming that the manganese 3,4 oxidation state with the antiferromagnetically coupling in nature. Okay, we form the intermediate. So what we can do, because you know this manganese bis-mioxo intermediate, which is actually presented, which is there as a one of the intermediate in the oxygen evolving complex. And in 1970s and 80s, it is believed that this is responsible for the abstraction of hydrogen from the water. Okay, so this bis-mioxo compound is responsible for the abstraction of hydrogen from the water much earlier. Okay, so then I thought, okay, this can be act as a intermediate for some organic substrates or not. Okay, so I tried to add water, but we didn't see any water oxidation. So then I have chosen an organic substrates like aldehyde. So this is 2-phenyl propane aldehyde. So in this case, what happens? So deformylation occurs, and we end up with the acetophenone plus formate as a product. Okay, so this is a nucleophilic reaction, and we also try to see whether this can act as a electrophilic oxidant or not. So we try to use this particular substrate, that's a 2,4 ditertiary butyl phenol, and we end up with the CC bond coupled product, and this is a OH bond activation product. Okay, so we are still working on the mechanism. How does it work? So we are not sure about the mechanisms. We are still working on this mechanism. Okay, so then after this work, then I try to see whether I can produce some of the manganese 5-oxo compound or not. As I mentioned to you that we borrowed some compound we purchased some compounds from Collins, this tetramido macrocyclic ligands, and we made a manganese 3 TAML compound. And this TAML compound, when we exposed to O2 in the presence of cyclohexene in acetone or acetonitrile, we could see the formation of manganese 5-oxo intermediate. So you can see here. So this is a UV visual spectrum. So the black line is for the manganese 3 starting complex. And when you expose to O2 in the presence of cyclohexene, so we see the formation of new peak at 430 nanometer, and this is corresponding to the manganese 5-oxo intermediate. And this 2 organic product has been confirmed by the GC and GCMS. And again, this manganese 5-oxo formation, after this formation, we have confirmed by mass spectrometry, and we can see that there is a very clean peak at 441 MIG value, and this is corresponding to the manganese 5-oxo TAML ligand. And then we try to see whether this oxygen is coming really from molecular oxygen or not. So for that, we have used the isotopically sensitive oxygen, that is 18 labeled oxygen. So when we use 18 labeled oxygen, this 444.1, it shifted to 443.1, and this is clearly confirming that this oxygen is coming from the molecular oxygen. And there is one oxygen which is present in the manganese center. And we have also performed a variety of we also performed this reactions with the variety of cyclic olefins, and we see the similar results. And we also performed this with the deuterated compound of this cyclohexene, and we see the kinetic isotopic effect for that. And based on that, we try to propose a mechanism, and manganese 3, which will react with the O2, and it will produce manganese 4 superoxide, and this superoxide will attract a hydrogen from this olefin, and you get a manganese 4 hydroperoxide unit. So we are sure that this superoxide is abstracting hydrogen from this olefin because we observe the kinetic isotopic effect of 16, and this could be the red remaining step of this particular reaction. And after this, so it undergo O bond cleavage, so we end up with the manganese 5 oxo compound. So if you look at here, so I put manganese triple bond oxygen. Sorry, here I should put manganese triple bond oxygen. So and here I put manganese triple bond oxygen. So interestingly, you know, we got the crystal structure, and this crystal structure shows the bond length between this manganese oxygen is 1.555 Armstrong, and this is an indication and very strong evidence for the manganese triple bond oxo character. Okay, and we also performed this resonance Raman spectroscopy to identify whether this has a manganese 3 oxo unit or manganese like a manganese oxygen is triple bond or double bond. So we try to identify with the resonance Raman spectroscopy. We see the difference between this manganese oxygen with the 18 labeled oxygens. We found it that 45 per centimeter is the difference. So we it is confirming that it has a manganese triple bond oxygen in nature. Okay. So then, as I mentioned to you that I was interested to make manganese peroxide with oxygen, and also to produce manganese hydroperoxide unit from that particular peroxide compound. So for this study, so I have made a manganese 3 13 TMC compound. So 13 TMC means it is nothing but tetramethyl cyclam ligand, so which has a 13 ring, and this is the tetramethyl cyclam ligand. So this cycle, so 13 TMC manganese 2 with a hydrogen peroxide and triethylamine, so it produces manganese 3 peroxo, and this manganese 3 peroxo which undergo aldehyde deformylation reaction. So that is known in the literature. And I try to examine this pathway. So I try to add triethylamine, and in the presence of O2, so I could see the same manganese 3 peroxide unit. And upon addition of proton to this intermediate at very low temperature at -40 or -20 or -10 degrees Celsius, so I can produce a manganese 3 hydroperoxide compound, this red color. Okay, and this manganese 3 hydroperoxide compound, which shows the reactivity with oxygen atom transfer reaction and hydrogen atom transfer reaction and aldehyde deformylation reaction. So these two, the green color reactions are electrophilic reaction, and this is nucleophilic reaction. So based on this, we say that this manganese 3 hydroperoxide has an amphoteric behavior. Okay, so you can see the spectral change. This black line is manganese 2, and it's a high spin manganese 2, so which means you should not have any UV visual spectral signature. So then upon addition of this triethylamine and O2, there is a new peak formation at 280 nanometer, and this is corresponding to the manganese 3 peroxide compound. And this manganese 3 peroxide compound, by the addition of proton, we see the new peak formation. So this is manganese 3 hydroperoxide compound. Okay, and these two intermediates are reversible. By the addition of again base to this, I can produce manganese 3 peroxide, and again if I add acid, so I can produce manganese 3 hydroperoxide compound. And this has been characterized by other spectroscopic techniques like EPR and DFT studies also. The DFT studies, this is the DFT optimized the structure, and it says that manganese has a spin state of S equal to 2. And all these methyl group are present in the syn position. Okay, so then we propose a mechanism. So for this formation of this intermediate manganese 3 hydroperoxide intermediate, so this cycle is known. So you have a manganese 3 hydrogen peroxide and triethylamine, and you can produce manganese 3 hydroperoxide. And this is what we have done it in this paper. So you know manganese 2 which will react with the O2, and manganese 2 will donate 1 electron to this O2 pi star orbital of oxygen. So this will accept 1 electron from this manganese 2, and it will become superoxide, and you will produce the manganese. Sorry, this could be manganese 3 superoxide compound. Okay, and addition of 1 more electron, so you produce a manganese 3 peroxide. Then addition of proton, you produce manganese 3 hydroperoxide. Then loss of 1 proton, you will get manganese 3 peroxide, and this is reversible. That's what I have shown here. Okay, and the reactivity also I have mentioned. So then we were actually successful in making manganese 3 hydroperoxide compound. Then I was thinking that whether we could produce manganese 4 hydroperoxide compound. So for that, we have actually taken manganese 4 peroxide compound, and we obtained this compound from Professor Lee from Taiwan. So we added proton at -65°C, and we see the new peak formation. You can see here. So the red color is corresponding to this manganese 4 peroxide compound and addition of 1 proton, and we see the new peak formation. Unfortunately, this is highly unstable. Even at -65°C, we could not characterize this intermediate by many other spectroscopic techniques. Okay, and we see the formation of manganese 4 peroxide compound. So we believe that it could be manganese 4 hydroperoxide compound. However, addition of a substrate and this manganese 4 hydroperoxide, we believe that it's a manganese 4 hydroperoxide compound, and this the proposed manganese 4 hydroperoxide compound, it reacts with the triphenyl phosphine. And once the triphenyl phosphine, if it is reacting, then I should get triphenyl phosphine oxide, and that triphenyl phosphine oxide, it is coordinated with the manganese, and we get this crystal structure. Okay, so based on this, we propose that this blue color line is corresponding to the manganese 4 hydroperoxide compound, and it has been published recently in Dalton transaction. Okay. So then, after joining here at NIT Calicut, so this is this work in collaboration with Dr. Duri, who is a speaker for this afternoon. You know, we have made this manganese porphyrin compound with the cationic positions. And interestingly, when we add iodosobenzene as an oxidant in aqueous buffer medium, and we see the new peak formation, and we propose that it could be a manganese 5-oxo compound. You see here, so this red color, so the red color is corresponding to the manganese 3 porphyrin. So generally manganese, not only manganese porphyrin, generally all the porphyrin will show you a typical spectra, 2 different typical spectra. That's a Swarad band and a Q band. And Swarad band, it will be a higher in intensity, and Q band you will be having lower in intensity. And for metal porphyrin, generally you will be having a 2 Q bands. Okay, for free base porphyrin, you will be seeing a 4 Q bands. Okay, free base porphyrin, you will be having a 4 Q band, and for metal porphyrin, you will be having a 2 Q bands. Okay, so upon addition of PHIO to this in aqueous buffer, and this red color is started decreasing, and we see the new formation of new peak at 422 nanometer. Okay, so this is the Q band difference here. And once we form this compound, so we try to see whether it is a manganese 4-oxo or whatever any other intermediate. Okay, so we postulated that it could be a manganese 5-oxo. Okay, by using a variety of organic substrates for this intermediate. So we added thioanisole and cyclohexene and like a xanthine for hydrogen atom transfer reaction. So we added cyclohexene to this intermediate, and you can see that this blue line is decaying, and we see the formation of 466 nanometer, which is again corresponding to this manganese 3 compound. So this is actually, you know, this upon addition of cyclohexene, we end up with the epoxide. That's a 2-electron oxidized product. We got cyclohexene to cyclohexene oxide. So and sulfur to sulfoxide. So this is a 2-electron oxidized product, and we confirm this. We confirm that based on the product analysis, we confirm that this blue line, it could be a manganese 5-oxo intermediate. And we published this work in New Journal of Chemistry, and in fact, this work was selected as a cover article for this issue. So I think I am done with my presentation. So if you are having any doubts or questions or any clarifications, if you need, you are welcome to ask me. Thank you.
Thank you, Dr. Sangaralingam, for your very nice and enlightening presentation on the topic. Now the session is open for discussion. Anybody have any query, you can post it. And Ms. Yamuna, if you receive some questions, please you convey to Dr. Sangaralingam.
Sir, one of the participant has posted a question, sir, in the chat box. In the slide 15, what is the source of electron for the oxygen activation to form manganese 3-OH compound in the final step?
So slide number 15.
Yes, sir.
So I mean, you mean here? Huh?
Yes, sir. Can you read it again, sir?
So this slide number 15. So you are asking that electron source for this one, right?
Yes, sir.
So actually what happened, so this manganese 2 compound, so this ligand is actually an anionic ligand. So I have added a triethylamine as a base. Okay, so we believe that the triethylamine is acting as an electron donor to activate the oxygen. I hope it is clear.
Yes, sir. Next question is posted by Dr. Shankar, sir. As various types of ligands used, can you correlate the effect of ligand donor with stabilization of high valent oxo species? And also, can you correlate with the nature strategy as mostly stabilized by amino acids?
Actually, so this is very difficult to say, because as a biomimetic inorganic chemist, so I would say that you have to play with a lot of ligands. So I was very happy that I made this particular monoanionic ligand, so I could get many different intermediates. So it's not like one can specifically say that okay, if you make this particular ligand and you can end up with many different metal oxygen intermediate. So that's it cannot be general, because you have to tune the temperature, you have to tune the solvent, you have to tune the oxidant. Okay, you have to play around. Otherwise, like it's not possible to generalize that this particular ligand system will work for all these intermediate. No. See, whatever I showed you now, it's almost 3 years of investment. 3.5 years of investment. So I played a lot with this particular systems. So if you look at that, I wanted to make with this particular compound, I wanted to make manganese 3 peroxo and manganese 3 hydroperoxo and even manganese 5 oxo, but it was not successful. So that means you need a special conditions, and you need to play around with the solvent. You have to tune the temperature and solvents, and many different conditions are there, so that you have to play around.
So in the absence of any other questions, I do thank again Dr. Sankaralingam.
Sorry, I have some queries.
Covers more knowledge on non-heme manganese compounds. Thank you very much.
Okay, so thank you. I think somebody is.
Yeah, I have some questions. This is Dr. Sukanta Mondal from IIT Kharagpur.
Oh, okay, yeah, please.
So, sir, please.
So first of all, it's a very nice talk and very nice work.
Thank you very much.
I have some queries, like in this slide, the DPAQ, that particular ligand. So when you have reacted with cerium 4, like you have some cerium 4 adapt.
Yes.
So in that case means this quilonin moiety is also very redox active. So don't you see any ligand based oxidation?
No, we didn't see, because if there is a ligand based oxidation means so it is actually a very nice question, because we also get this question by the reviewer. But so if the ligand is getting oxidized, it means so we will have some radical. So that radical could be easily trapped by EPR spectroscopy, right? So we didn't see any.
But it should be a metal center radical. So that may not be, means it is not that it is a localized radical. It may be a metal and ligands, they can interact with each other. So in that case, it may not be easy to detect by EPR sometimes. Means you may not get in. There should be some influence by the metal as well. Because I have seen some papers with the same ligand system, but they have used some different metal. I don't know, remember exactly what metal, but they have reported that they found some ligand-based oxidation as well.
Okay, so so if there is a ligand-based radical, so I can also support by using EPR as well as by the resonance Raman. So this resonance Raman stretching frequency, it says that it is actually a double bond in character. The manganese oxygen, the bond distance is a double bond in character. So we will not get in that case. So because if you have the radical character, so this actually it should be a single bond in nature, right?
Means how do you confirm that it's a manganese 4? Why not it can become a manganese 4 and then quinoline radical? So formally
No,
it
we
can be
can.
manganese 5.
Okay, so manganese 4 we confirmed by using EPR spectroscopy, which I did not show you here. So EPR spectrum, it shows that it is manganese 4. It is not manganese 5.
Okay, and here you have used the can in a stoichiometric manner or in excess?
Actually, so we have done the titration. I did not show you the titration. So we need actually a stoichiometric reaction.
Okay, and
Yeah.
one of your reaction, the KI value you have shown here around 16.
Yes, yes,
yeah,
yes.
so that is I think very high value of because means do you think here some tunneling is happening? Because sometimes I think so that if the KI value
So
is very
I
high.
also believe, yes, it is very nice observation from you. So I also believe that there is some tunneling effect is involved here, because generally when you have more than 10 or more than 12 KE, so people used to say that there is a tunneling effect, but we did not say anything about that. So we just say that it is a rate determining step of. We just say that the hydrogen atom transfer is the rate determining step. So we didn't mention anything about the tunneling.
Okay, and one more thing, this particular manganese 5 oxo, triple bond oxo.
Yes,
so you
yes.
have a very nice crystal structure. So
Yes.
does this compound means have you checked its reactivity?
Okay, so so this crystal structure we have obtained at room temperature, so it is not reactive.
Okay, it's not reactive. It's so
yeah,
stable.
that's the reason we got. That's the reason we got actually a crystal structure.
Yeah, but it's so stable. But if you suppose in this case you don't have any axial ligation, so that makes that manganese triple bond oxide very stable or very impact.
Yeah,
so
see,
if
actually
you put
what
some,
happened.
yeah, if you put some coordinating ligand, external ligand, which can coordinate through your axial site, then in that case your manganese 5 oxo, that bond may be little bit weakened, and then it we can make it much more reactive.
Yes,
So
yes. It's a very good suggestion. We performed actually a similar reaction by adding a different metal ion. Okay, so we actually end up with the scandium bounded species. Okay, actually in the same JAX paper we also have the another part. Okay, when we add scandium triflate, so it binds with the ligand oxygen unit, and actually the potential of this manganese oxygen, it becomes very higher and it shows reactivity. So we try to add some external ligands like axial effect or some metal-ion bounded effect. So we try to add, for example, scandium. So it binds with this scandium. It binds with this amide oxygen, not with the oxo, because you know that it is more basic than this oxo unit. Yeah. So that has been already reported. So. Yeah. Thank you. Very nice questions and very nice.
One more small query I have. So you have shown some crystal structure of manganese 3 hydroxide and manganese 3 water.
Yes.
I think it is a slide number 14 or something.
Yeah. Yes.
So here the bond distance difference you are seeing means is that there means this, as it is a manganese 3, so I would expect some gentler distortion, so axial elongated things. So the axial portion means in octahedral all positions are equivalent. So whatever difference you are seeing is that position has been changed, means that now this aqua things, it may not be considered as axial. Some other bond distance can be considered as an axial. So means my question. So my question is that this difference is due to this protonation, or it has changed the axial positions, or we can consider the axial things in other way. That's why you are seeing this difference.
Okay, so actually, so we did not look into much, carefully into all these bond lengths. So we just focused with only this manganese oxygen. I will look into that.
Okay.
Thank you.
Because
nice
as it is a manganese 3, and I think it is a high
yes,
spin.
Yes. I got your point, and very nice suggestions. I will look into that.
Okay. So thank you very much.
Thank you. Thank you very much. Thank you.
So a few more questions are posted in the chat box, sir.
Yes, please. Yes.
First question is, how did you predict the manganese 4 complex needed for that before doing the experiment?
Can you repeat your question, please?
I mean, how do you predict the manganese 4 complex needed for the experiment?
How did you predict or protect?
Predict, sir. What type of complexes can we use for this particular experiment? They're asking.
Okay,
that.
see, actually, so I mentioned to you, so in this slide, so I mentioned to you, so there are many different manganese oxygen intermediates which are proposed in this Koch cycle. So I mentioned to you that I am very much interested to see whether I can able to make this intermediates by using mononuclear compound or not. So that's the reason I designed some ligands and I try to see whether I can produce or not. So I was successful in making, I think, this manganese 3 hydroxo, manganese 4 and manganese 5 and manganese 3 hydroxo. I think, is that okay? This answer is, I hope it will be okay with you.
Yes, sir. And again, there is another question, sir.
Yes, please. Yes.
What is the absorption feature on which the laser is tuned for doing resonance Raman to resonance enhance the manganese 4 O bond?
Okay, so this is a very nice question, but so this generally we perform this resonance Raman based on our this absorption of our particular compound, absorption spectra of our particular compound. See, for example, this particular compounds as absorptions in between 400 to 800. So we try to utilize, I think, 405. I didn't mention here what is the excitation we use. I think it is 405 we used. So probably we can change the wavelength. We didn't try it. We can change the wavelength. I think it should be the similar result.
Okay, in the absence of any other question, we do thank again Dr. Sangaralingam for his excellent presentation and patience in answering all the questions raised by the participants. Thank you very much.
Thank you very much. Thank you very much for giving me an opportunity to present my research work. Thank you very much for the organizer and convener, my friend Dr. Sundaravel. Thank you. Thank you very much.
Thank you, Shankar.
Yes.
So we will meet again after lunch. Thank you.
Thank you. Thank you. Thank you. Thank you.
All the participants are requested to again join the webinar around 2:15 and we'll be resuming the session around 2:30. Thank you.